So our next topic will be lines in space, though, right? So hopefully you're all familiar with lines, at least in a plane, in the xy plane, for example. You know how to describe a line, mathematically anyways. But now we're dealing with a line in space, and so each point on this line will have three coordinates, x, y, and z. Okay? So our goal is to describe, right, the set of points that make up a line. Right, so we'll call it line L, let's say. Right. So what do we need in order to describe this, this line? Well, we either need 2 points on the line, right? So we can describe another point as, say, x naught, y naught, z naught. So that this will be a given point. Right? And a second point, right? So that's one possibility. But all we really need is a point and a direction, right? What direction is the line going in? So we can describe that direction by using a vector. And maybe I'll treat that. Yeah, so this will be a vector v. And it'll be a vector in space, right? So it'll have 3 components. And typically we'll use, v1, v2, v3. But the book switches this up a little bit, and the components are now A, B, and C. So I hope that's okay. So A is the first component, the X component, B is the Y component, C is the Z component, right? And they're just numbers, right? They just represent numbers, scalars, right? So now we can think about any other point as just being, so we have some origin here, let's say 0, right? So this is the point 0, 0, 0, right, which we just call the origin. And we can form a vector from the origin to the given point. And so this vector, I guess for now, let's just call it W, which is the vector with components, x0, y0, z0. Okay. And our goal then is to describe a vector from the origin to any given point on the line, right? So I guess this will be, I don't know, call it vector u. Actually, I'd rather call it r. And this will come up again in the next chapter. So r will have components x, y, and z. And the key is that, right, we can form a vector, and I'm sort of running out of colors here, but we can have a vector now from, let me erase this vector, from the point, so starting at x0, y0, z0 and ending at x, y, z, right? And it's really just a multiple of v, right? So this vector, all right, so hang on, let me move this around a little. Okay, so the little blue vector here is still ABC, and again, this is a given vector, right? As well as the given point right here. So now this green vector is just some multiple of v. So it's c times v. But we're not going to use c here. After all, we're already using c as the component. So we'll use t times v. Okay. So I think if we add the vector w plus the vector t times v we get the vector r, right? Parallelogram, right? So that's it. Now, of course, r will depend on t now. It'll be a function of t. And it's going to be the vector, well, w plus tv. But let's write this out in terms of the components now. In terms of the components, the vector w is x0, y0, z0, plus t times the vector v, which has components a, b, and c. Right? And, okay, I'll go step by step here. This is x0, y0, z0, plus, and then the vector, right, this is just scalar multiplication. When you multiply by t, you just multiply each component by t. So ta, tb, tc. And then when you add these two vectors, you get x0 plus t times a, or a times t. And then the second component will be y0 plus t times b, or b times t. The third component will be z0 plus c times t. Right. And that's my vector r as a function of t. Right. And so for any given t, that describes a particular point on the line. After all, if t is 1, then it describes, well, I don't mean to erase it here, that describes this red point right here at the tip of v. If t is 2, then that's twice as long. T is 3, right? Then you go 3 times as far, and so on. So in this picture, t is somewhere between 2 and 3. All right, so that's it. If I want to describe the x-coordinate of this point right here, it's just going to be x0 plus a times t. The y-coordinate will be y0 plus b times t. And the z-coordinate will be z0 plus c times t. Okay, so these three equations tell you where you are on the line, what point you're at on the line, on line L. Right. And if it's an infinite line, t could be anything, right? T could be any real number. Right. If you only want to describe a line segment, say from one point to another point, right, then, t might range from, say, a to b, right, between two specific values, right? Or if you want to describe a ray, like half a line, you start at one point and then it goes forever, then t might be greater than or equal to a, greater than or equal to if you include the point, right? Yeah, so for an infinite line, t can be any real number, right? So these form what are called the parametric equations of a line. And we will use these extensively. Right? And of course, you can also use them to describe a line in a plane. In that case, there is no z-coordinate. It's just x and y. Right? And you've probably seen that before back in Calc 2. But that said, here we're describing a line in space. And so a line in a plane is just a special case of that. Right. And so there's another way, another set of equations that we can use to describe a line. And those are called the symmetric equations. And the way to derive these is just take each of these equations here and solve for t. So if you solve the first equation for t, you get x minus x0 divided by a. If you solve the second equation for t, you get y minus y0 divided by b. And if you solve the third equation for t, you get z minus z0 or z0 divided by c. And the point is, it has to be the same t for all three equations. If the t is different, then you're not on the same line. You might be on a different line, right? So these are three equations. We're just writing them all at once. You know, well, hopefully you can see that there are three equations, right? Here's one equation, right? Here's the second equation. And then here's the third equation matching the x and z. Oh, I didn't highlight the equal sign here. So that would be the third equation. So here you're just writing it all at once. Right? So for the symmetric equations, though, there's no t anymore, right? We're essentially eliminating the t. So this describes it more geometrically. As we'll see in the next chapter, the parametric equations are a good description of a point moving on a line. So parametric equations are good for describing motion, something moving. The symmetric equations describe just the line itself. Okay? Right, so I think we're ready for our first example. Okay, so we want to find a set of parametric equations, and while we're at it, symmetric equations, for the line passing through two given points. Right? So it only takes 2 points, say P and Q, right, to determine a line that passes through them, or pretend it's a line, right? And yep, and these are the coordinates of each point. So if you're given 2 points, how do we find the parametric equations? So yeah, the parametric equations are up here, right? So for the parametric equations, we were given 1 point and a vector. Here we're given 2 points, but no vector. Okay. So what can we do, right? What's our x, y, and z? Well, just to remind you, it's x0 plus at, y is y0 plus bt, and z is z0 plus c times t. So what we're looking for are x0, y0, z0, and a, b, and c. So x0, y0, z0, right, are the coordinates of any point on the line. And look at that, we're given two points. So take your pick, either P or Q. I'm gonna pick P, right? So I'm gonna pick P to be my x0, y0, z0, right? So in this case, x0 is -7, y0 is 2, and z0 is 3, right? And what about a, b, and c? So a, b, and c are the components of a vector pointing in the direction of the line. Well, we're not given such a vector. However, we have 2 points, and we can form the vector from one point to the other point. So we have the vector from P to Q. Let's call that V. Right? And what are the components of V? Just subtract the coordinates, right? -4, -7. Oh, maybe I'll actually write them out. We have the space here. So V, which is the vector from P to Q, right? So -4 minus -7 for the x component, 0 minus 2 for the y component, and 8 minus 3 for the z component. So we're going to get 3, -2, 5. Okay, so that's my A, B, and C. Right? A is 3. Well, let's write it out. A is 3, B is -2, C is +5. So that's all we need. Now just write down the parametric equations, right? It's going to be x equals x0, which is -7, plus a times t. A is 3, so x equals -7 plus 3t. Y is going to be y0, so 2, plus b times t. B is -2, so 2 minus 2t. And then z is going to be z0, which is 3, plus 5 times t. And there's our set of parametric equations. So that will describe any point on this line, on this yellow line over here, right? right? So that's all it is, right? If you have 2 points, you can always form the vector between them and use that as your direction vector, right? So v is very often called the direction vector for the line. Because it points in the direction of the line, right? Right. So remember earlier I said for your x0, y0, z0, for your initial point, we could have picked, instead of p, we could have picked q instead. And so if you pick q, you'll get, well, you'll get a different set of equations, right? It will describe the same line, but you can also use -4 for your x0. You can use 0 for your x0. Oops, -2, right? And you can use 8 for your z0. So you get a different set of equations. However, it's the same line, right? So yeah, you have to get used to this idea. That's why it says find a set of parametric equations. It doesn't say find the set of parametric equations because there's more than one. In fact, there's essentially infinitely many, right? We could have picked any other point on this line. Now there were only 2 that were given, but at this point you can find any other point on the line. Just plug in a specific value of t, right? Right. And the vector v that we used here, right? That was not unique either. We could have picked a vector that's half as long, right? Or a vector that's twice as long, or maybe a vector that points in the opposite direction. So the components would just get flipped, right? -3, +2, -5. And that would also change the set of parametric equations, right? So yeah, should I even write down one of those as well? So it could have been x equals -7 -3t, y equals 2 + 2t, and z is equal to 3 - 5t. And that would also be a perfectly good set of equations to describe the exact same line here. Right? So yes, the equations are not unique for a given line. Right. So that's parametric equations. What about the symmetric equations? Because they wanted both. So remember how that works. You just solve each equation for t. And now the question is, well, which sets, right? Do I use the green set, the blue set, or the red set? And it doesn't matter, right? You're gonna get what looks like different equations, right? So even the symmetric equations are not unique for a given line. So just pick one. How about the green one, right? So for the symmetric equations, if you solve that for t, you get x + 7 over 3, and that's got to equal y - 2 divided by -2, and that's got to equal z - 3 over +5. And there's your set of symmetric equations. Okay, so as a practical matter, right, how do you find a line? You need 2 points or 1 point and a vector pointing in the direction of the line. And then you just use either the parametric equations or symmetric equations. And typically, I would find the parametric equations first because it's always easy to convert that to symmetric equations. On the other hand, if you want to go from the symmetric equations back to the parametric equations, that shouldn't be hard either. Just set everything equal to t and then solve for the x, y, and z, and that'll give you back your parametric equations. Okay, so those are lines in space. So now we move on to planes. Right. So when I say the word plane, I'm not talking about, airplanes. I'm talking about like the XY plane, right? But it doesn't have to be the XY plane. It could be any plane in space. So it could be this plane, right? Or this plane. Or trying to do something, this plane here, right? And of course, these are not the entire plane. These are just a piece of the plane, because a plane, like a line, extends infinitely in all directions. But then then I couldn't be able to draw it if that's the case. So I'm always going to draw just a portion of the plane or a piece of the plane, recognizing that these planes extend infinitely in all directions. We're only drawing a small piece of it, right? So now we want to describe a plane mathematically, just like we did for a line. Okay, so I'll pick this plane to describe mathematically. So what do we need to describe a plane? So it turns out we need, well, first of all, we're looking for any point in the plane, right? So I'll have this green point here and label that with coordinates x, y, and z. Okay. So if we had 3 points in the plane, 3 points that are not on the same line, that would describe the plane, right? So 2 points only give you a line. You would need 3 points to get the plane, right? To get a plane that those 3 points lie in, right? Yeah, but it turns out we only need 1 point, and again, we'll use x0, y0, z0, right? Z0. And you might think, well, okay, so you need 1 point and what else? Because 1 point does not describe a plane, right? You need at least 3 points. Or a point and a vector, right? So just like for a line, we had 1 point and we had a vector. So now the problem is that you can't just have a vector that lies in the plane, right? If you think about that, a point and a vector, let's say this point here, well, that does not determine a plane either, right? Because you can have a plane that like this, that contains this point and vector, or you can have a plane, think of like a vertical plane, like this, straight up and down. That also contains this point and this vector. So there you go. One vector in the plane does not determine the plane, right? So it turns out what we need is a vector not in the plane, because there's a lot of those, right? We need a vector pointing out of the plane, or perpendicular to the plane. So this will be a perpendicular vector. Again, we don't use the word perpendicular here. We use the word normal to describe a vector that's perpendicular to a plane. So this will be a normal vector, right? So it points in a direction, right, that's perpendicular to the plane. So this would be a right angle right here. Okay. So a normal vector, right? So if it's a vector, we'll call it n for normal vector. And the components will be, well, let's just use a, b, and c again. As long as you don't get confused with the same components for a direction vector for a line. So yeah, we use the same a, b, and c for a direction vector for a line. But this is not a line, so I think we're safe here, right? All right, so now our goal is to figure out a vector from the origin, right, to this vector here, right? And, well, we can certainly draw a vector from x0, y0, z0 to that point. And in fact, let's use the letter u here, right? Not for unit vector, but it's a vector. And the components will just be x minus x0, y minus y0, and z minus z0 when you subtract the coordinates, right? So what's the relationship between the normal vector and this vector u here? I'm going to erase all this stuff because it's a little bit of a clutter at this point. So hopefully you can see the relationship. This blue vector u lies in the plane. And I know that because it's from one point to another point. Both of those points are in the plane. But the vector n, of course, is orthogonal to the plane, or it's normal to the plane. It's orthogonal to the vector u. Right? So this is also a right angle. Right? So we know that n and u are orthogonal. Right? Or perpendicular, if you prefer, but the correct terminology here is orthogonal. And what do we know about orthogonal vectors? Right? Think about the definition of orthogonal. Right? N and u are orthogonal if their dot product is 0. Okay? That's what it means to be orthogonal. Right? And if we can take the dot product and show that it's equal to 0, then we know that the two vectors are perpendicular or orthogonal. Okay, so let's write this out in terms of their components now. N has components a, b, and c, and u has components, well, x minus x0, y minus y0, and z minus z0. And we know, because they're orthogonal, that has to equal 0. Now let's just follow the definition of the dot product, right? You just multiply the components and add them up. So you multiply a times x minus x0 plus, right, b times y minus y0 plus c times z minus z0. And that has to equal 0. And there you go, right? This is as good of an equation as any to describe a plane. Right? So this is the equation of a plane. And it is, well, I should say it's an equation. There are many different equations that will describe a plane. The same is true for lines too, right? So this is an equation of the plane, right, containing the point x0, y0, z0, right, and it's normal to, right, that means perpendicular to the vector v, I'm sorry, not v, n for normal vector, the vector n with components a, b, and c. So once you can identify the normal vector with the three components and any point in the plane, then you have your equation of the plane. Okay, and that's supposed to be a z here. Yep. Okay, so I guess we'll just start with an easy example here. Okay, so we're going to find the equation of the plane containing the point 8, -2, -6, and normal to the vector 2i minus 3j plus k. And again, that's right in component form. You can say 2, -3, 1. Same thing. Right. So we have all the information, right? This, what we're given is the normal vector a, b, and c, and the coordinates of a point that's in the plane. So you're just plugging these into the equation of a plane. So let's do that now. So a is 2, so 2 times x minus x0, x0 is 8, plus b is -3, times y minus y0, y0 is -2, and then c is 1, so plus 1 times z minus z0, and z minus -6. And all of this, -6, equals 0. Right. Now, please don't leave it like this, because it's kind of a mess, right? We got to simplify it. So first of all, we have, this is a -3 times y plus 2, and this is just plus z plus 6. Okay. Now let's distribute the 2, so 2x minus 16. Let's distribute the -3, -3y minus 6, And, well, distribute the 1, so it's just z plus 6, right, equals 0. So we certainly can add the numbers here. We have negative 16 minus 6 plus 6. Well, that's just negative 16. So all we really have is that 2x minus 3y plus z minus 16 equals 0. Okay. So right up here in green here, what's boxed in purple, that's the given equation of the plane, but you don't want to leave it in that form, right? You always want to simplify it, right, from this form to this form. And in this form, we can, right, so the a, b, and c are still the same. This is still ax plus by plus cz. And then this number here, the negative 16, we'll call that d. And that will equal 0. So this, let's call this the standard form, or the standard equation of a plane. And I hope I didn't call it a line. It's a plane, not a line, right? So yes, this given equation here, a times x minus x0 plus b times y minus y0 plus c times z minus z0, right? That's the form that you get after plugging in the numbers, right? That's what we did right here. But then you just got to multiply it out and simplify. It's just a little bit of algebra, a little bit of really arithmetic. And then you put it in the standard equation of a plane, the standard form of the equation, right? So this is the form that your equation should look like. And in some cases, you can even, if you're careful, you can even write it this way. 2x minus 3y plus z equals 16, right? So you can add the 16 to both sides. Just be careful, because then you might be tempted to say that d is 16. Unfortunately, right, we know that d is negative 16. So the d is not the number on the right side of the equation. It's this number here. It should be on the left side. Okay, and it does make a difference in some cases whether you say d is 16 or negative 16, because that would give you a different plane. Okay, again, that's a very easy example, and then we'll get to some trickier examples in a minute. Okay, so we want to find the equation of the plane containing these 3 points: 1, 2, 1, 4, negative 1, 2, and 5, 3, 0. And so P, Q, and R respectively. Okay, so you just imagine this is space here, and we have these 3 points, P and Q, and then R. Well, if R lies on the same line as P and Q, then that's not going to work, right? So we have to convince ourselves that these 3 points are not collinear, right? That they don't lie on the same line. And if they don't, then we have a plane. So we're looking for the equation of this plane containing these 3 points, right? So what do we need to describe a plane? Well, remember, here's the equation. Just writing it down. And again, you don't have to memorize this. It's on your formula sheet. So you can just look at, refer to it or look it up. So what do we need? Well, we need x0, y0, z0, and we have that. In fact, take your pick. We have 3 points. So which one you want to be your x0, y0, z0 really doesn't matter. So I'll pick the first one, point P. So x0 is 1, y0 is 2, z0 is 1. But if you picked Q or R, that's fine, right? In the end, you'll get the same equation, although it might, well, I mean, like I say, it might look different, but we can put it into the same form. So the standard form of the equation will be the same, right, for no matter which point you choose here. All right, what else do we need? We need A, B, and C, right? In other words, we need a normal vector n. And that we are not given. We're not given any vectors, right? So how am I supposed to find? Oh, that doesn't look perpendicular, does it? Something like, how about just straight up, right? So that's going to be perpendicular to the plane. How are we going to find this normal vector? So notice that we have two other points, and we haven't used those points yet. Right, so it looks a little confusing. How am I supposed to get a vector from these 3 points? So think about that for a minute. Remember, when you have 2 points determines a vector. So let's say we have the vector from P to Q. And I'll just call that vector U. Again, not a unit vector, or it doesn't have to be a unit vector. And we have another well, we have a choice. We can use Q and R, but I'm going to choose P and R for my second vector. And we'll call that vector V. So both vectors U and V lie in the plane. Right? So U and V lie in the plane. So now, it should be clear, at least I think it's clear, how to find n. Think back to the last section, the last video we did, right? How do you find a vector perpendicular to two other vectors? Or I should say, a vector orthogonal to two other vectors. Yep, so the answer is take the cross product. The cross product will always be orthogonal, right, to both vectors. So my vector n, and I'm just going to slide it this way here so I can erase this vector here, will be orthogonal to both u and v. And if u and v are in the plane, then the vector n will be orthogonal to the plane. Or I should say normal to the plane, right? N is normal to the plane. Okay, right, so the vector u, and we should write this down here. The vector u has components, well, it's from P to Q. So when we subtract the when we subtract the coordinates, we get 4 minus 1 is 3, -1 minus 2 is -3, and 2 minus 1 is 1. And then the vector v will have components, let's see, from P to R. And so now subtract the r, so 5 minus 1 is 4, 3 minus 2 is 1, and 0 minus 1 is -1. And so these are the three components of the vector v. And again, it didn't matter that I chose the vector v to be from P to R. We could have chosen from Q to R. And while that might give us a different set of vectors, in the end, the normal vector will either be the same or it'll be, just a multiple of the other. It'll be pointing in the same direction. All right, so now we have enough information to get the cross product. And again, you imagine your determinant here, I, j, and k, and then just take the determinants, right? So 3 minus 1 is 2, 4 plus 3 is 7, and then 3 plus 12 is 15. So A is 2, B is 7, and C is 15. Right, 3 plus 12, yep, 15. Okay, so I'm just making sure I got this right. So it looks right to me. Again, if you're getting -7, then you forgot that you're using the wrong determinant. The determinant, remember, you have to alternate. So this will get a minus sign. So it's minus -7, right? Which is +7. So just be aware of that. Okay, well, now we have our a, b, and c, and we have our x0, y0, and z0. Now we can just find the equation. So it's going to be 2 times x minus x0. What was x0? 1. So 2 minus 1. And then plus b, which is 7, times y minus y0. Y0 is 2, plus, 15, because that's c. Z minus z0 is z minus 1, right? And that equals 0. So this should be the equation of the plane. And, well, maybe we should multiply it out, right? So 2x minus 2 plus 7y minus 14 plus 15z minus 15 equals 0. And then 2x plus 7y plus 15z. And then we have negative 2 minus 14 is negative 16. Negative 16 minus 15 is negative 31. So that's our standard equation of the plane, standard form. And that's supposed to be a z here. I think I can fix that. Just start over. So this is 15 times z. I know my z's look a little funny here. But I don't like writing z's like this because it almost looks like a 2. So I try to put a little line through the z here to indicate that it's a z rather than a 2. You're welcome to do the same, but just be careful. If your z's look like 2s and I can't tell which one is which, you can lose a point for something as awful as that. So just make sure you distinguish your 2s from your z's by doing something like that. Okay, so that's it, right? So if you have 3 points determines a plane. Little trickier because to get the normal vector, we have to use the cross product, and we have to form these vectors here in the plane, then take the cross product, and that gives you your normal vector. Okay, so, right, and you can try if I used Q and R instead of P and R to get a different vector, and then a different, you might get a different normal vector, but in the end, you're going to get the same equation, right? So just as a warning, though, if you get an equation like this, and say, well, then I must have done something wrong because I don't have the same equation as you. These are different equations. Well, of course they're different equations. They're not the same equation, but they do represent the same plane. Okay, so this is a little different than when we talked about lines. The parametric equations of a line are not unique. And of course, the equation of a plane is not unique either. But it is unique in the sense that, just notice that if you just multiply the first equation by 2 times 2, then you get the second equation. So when you see this, I would be tempted to notice that all of these coefficients here, all these numbers, are multiples of 2. So to simplify, why not just divide everything by 2? And by doing that, you end up with the exact same equation we had. Equals 0. Don't forget equals 0 because it is an equation. And it's the same one, right? So yeah, so when you reduce everything down, right, you should get the same equation. But again, I would accept either. Of course, I would accept this equation too. I would just recognize it as just twice the first equation. That's all. Okay, we'll do another one. Okay, so find the equation of the plane containing the lines, and I'm not going to read them. You can read them for yourself, right? So you have x, well, okay, I'll read them. The first line, which we'll call line, I guess, L1, x equals 3 minus 2t, y equals 1 plus 4t, 4 times t, sorry, and z is equal to 2 plus t. And then line 2 has parametric equations x equals 1 plus t, y equals 5 minus t, z equals 3 plus 3t. Okay. So yes, one line does not determine a plane, right? Because there's many planes, that pass through this line. There's this one, right? There's also this one. So yeah, one line does not determine a plane. However, you can imagine if there are two lines and they're not the same line, then that should be enough to determine a plane. Oh, okay. I hope that helps. So we're looking for the equation of this plane. And I don't want to use p for plane. If you want a symbol for plane, how about pi? So yeah. So what are we given? We're given two lines. And what do we need to find the equation of a plane? Well, here's the equation again, right? A times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. So we need a point. We need x0, y0, z0. And we need a normal vector, n. So a, b, and c. So how do we get those? So in some sense, we're given, way more information than we need. We're given a lot of points. Take your pick, right? Right. So I would not pick, say, this point here. That might be pretty tricky to find, right? We're given two lines that are in the plane. So why not pick a point on one of the lines? So we'll call that my point P, right? Which is x0, y0, z0. So what point should it be? Well, if this is line L1, right, pick any t you want. Any t you want. How about t equals 0? Right? That's an easy one. If t is 0, then you get x equals 3, right? Y equals 1, and z equals 2. So we'll use those as my x0, y0, z0, right? 3, 1, 2. Got it? Okay, well, now we need the normal vector, right? And how do we find the normal vector? So any vector perpendicular to the plane. And notice that it's going to be perpendicular to both lines L1 and L2. I'm trying to draw a little square here. It's not looking right. That's a little better. Right? And so, right, these are lines, not vectors, but we can easily come up with a vector, right, that points in the direction of each line. Does everyone see how to do that? So it's just the A, B's, and C's, the multiples of t here, that form the vector. Right? So, originally we wrote this as, x0 plus a times t, but then the a, b, and c formed the components of a vector in the direction of, say, L1. And likewise here, these three coefficients will be a vector, I'll call it w, in the direction of L2. Okay? So what is v here? Well, -2, 4, 1. And w, 1, -1, 3. Okay. So those are two vectors that, well, they lie in the plane because they lie on the lines that are in the plane. So to get our normal vector, we do the usual thing. Oops, a little more space here. Yep, take the cross product, v cross w. Oh, if you ask, well, what if I did it the other way? What if I did w cross v? Would that be okay? Sure, no problem. Remember what happens when you switch the order of the cross product. You don't get the same vector. You get a vector pointing the other way. You get essentially -n. But that's still a normal vector. There's nothing wrong with using that vector instead, right? Any multiple of n, right? 2 times n, 12.5 times n, or even -1 times n is a perfectly good normal vector, right? So so yes, w cross v would have worked as well. But since I wrote it down this way, I'm going to use v cross w, if that's okay with you. And we get 12 plus 1 is 13. 1 plus 6 is 7, and then 2 minus 4 is negative 2. I know I did that fast, but at some point you should be very comfortable with thinking of it in terms of the determinant. Again, if you want to do it just based on the formula for the cross product, that's fine. Personally, I don't remember that formula. I remember the determinant version of that. So, right. So this is our A, B, and C. And now you have to be careful because just maybe 5 minutes ago I said A, B, and C was negative 2, 4, and 1. That's obviously a different A, B, and C, right? So yeah, so we're using A, B, and C for different things here. For the direction vectors, say V and W, and then we're also using A, B, and C for the components of the normal vector. So I hope that's not too bad here, but yes. So the A, B, and C that we want for the equation of the plane, that's this thing here on the left, are these three numbers here. Okay, so maybe let's just write them down, right? A is 13, B is 7, C is negative 2. Plug these into this equation and we get our plane. Well, we get the equation of the plane, right? So let's see, 13 times x minus x0. So 13 times x minus 3 plus 7 times y minus y0. y0 is 1. And then plus c, which is negative 2, times z minus z0. z0 was 2. Right, positive 2, yes. Equals 0. Right, so that equals 0. And now don't forget to multiply it out, right? So yeah, please don't leave it like this. You got to multiply it out. So what do we get? We get negative 39. Oops, sorry, negative 39 minus 7, and then plus 2. So negative 39 minus 5 is negative 44. Just make sure that's right. Yeah, I have it different in my notes. It's not 44. Oh, okay. I think I got it. Negative 2 times negative 2 is not 2, right? So this last number here should be a 4. 4, not 2. There we go. All right, so that equals 0. So, yep, it's 13x plus 7y minus 2z. And then negative 36 plus 4 is negative 42. Sorry, negative 46 plus 4 is negative 42. Equals 0. Okay. So that's the equation of the plane containing these two lines. And I guess we'll do another. Actually, maybe before we do another, let's get the concept of the angle between two planes. So if we have two planes, let's say this one here, and then a different one, say this one here. And you can see that the two planes intersect in a line. And that's actually a good problem. Given two planes, find the line of intersection. If we have time, we might even do one of those. But right now we're looking for the angle between the two planes. So that's this angle here. Let's just call it theta. Or you can use this angle here. What you don't want to use is the big angle, this angle here. That'll just be pi minus theta. So if your angle is obtuse, just subtract it from 180 degrees or pi radians and you'll get an acute angle. So you can always form an acute angle between two planes. Okay, so how do we find that angle? Well, presumably we're given the equations of these planes. equations, right? And if we're given the equations, we can easily find a normal vector, let's say n1 for the blue plane, and then we have another vector, normal vector, to the green plane. We'll call that n2. Okay. So notice that all we're going to do is just rotate the whole picture 90 degrees, right? So this angle here is the same as these two angles here, right? Just flip it 90 degrees, rotate it 90 degrees this way. So it's really just the angle between the two normal vectors. Okay, so the angle theta, right, and it's going to be between 0 and 90 degrees. Well, it could be equal to 0, but then the two planes would be parallel. And it could be equal 90 degrees if the two planes were perpendicular. So the angle between two planes is just the angle between the two normal vectors. The two normal vectors. Right. In this case, I'm calling them n1 and n2. Right? And these are not components, right? They're already vectors. I just don't want to use two different letters to describe a normal vector. That's all. I mean, you can use, you know, NA and NB if that bothers you, right? So let's call this plane A and this plane B. So, yeah. So how do you find the angle between two vectors? Yep, that was a couple videos ago. That's the dot product, right? So the cosine of theta is just NA dot NB divided by the magnitude of NA, sorry, that's an A, times the magnitude of NB. Right. Presumably the normal vectors are not unit vectors, so that's why you have to divide by their magnitudes. If you know that they're unit vectors, then you're just dividing by 1. So you can just take the dot product. Okay, so, yep, so you already have this formula. Well, you have it for any two vectors. You know how to find the angle between any two vectors, v, you know, u and v, let's say. Right, so that's on your formula sheet. But now we're using the u and v happen to be normal vectors, say n1 and n2. Write them as vectors, right? Okay, so that's not hard. So the next thing we want to do is find distances. And I think rather than derive these, I'm just going to write them down. I'd rather do more examples of them than to derive them. Well, okay. Maybe I'll do both. So here's a plane. So we have some plane in space. And we have some point. I'll use this red point here. So this point here will be, I'm going to use the letter Q, and it'll have coordinates x0, y0, z0. And this point Q is not on the plane, right? It's not in the plane. And if it's not in the plane, it's some distance away from the plane, right? So what we're looking for is how far from this plane is the point Q? If I'm going from the point directly to the plane, and I land right here, what is that distance? So I'll call it D for distance. Okay. Right, so yeah, so we're given the point, and presumably we're also given the equation of the plane. It's a B. In the standard form. Right, so we have the equation of the plane and we have the point, right? Find the distance between them. So this is distance between a point Q, and again, that point will be given. The 3 coordinates will be given. I'll clean up my Z a little bit here. Okay. And the plane, ax plus by plus cz equals, plus d equals 0, right? The standard form of the plane. So that's what we're going to try to figure out. And before we do that, you might say, wait a minute, if I take this point way over here on the plane and I measure that distance, isn't that going to be a lot longer than this distance d? How can I, right? So if I use a different point, I'm getting different distances. So how can I say the distance and not a distance? So sure, I can use a different point and you get a bigger distance. But notice that this point here is the closest point to Q. It's the nearest point. And so this distance d will be the shortest of all the distances. If I pick any other point on the plane and I measure that distance, say capital D, that will be bigger than little d. Okay, so what I'm really looking for is the minimum distance between a point and the plane. Okay, so right, so yeah, I should have the word minimum distance here, but we're never going to say minimum distance. It's assumed that when we say the distance between a point and a plane, we automatically mean we're looking for the minimum distance, okay? All right, so now we can see if we can figure it out, right? So notice I have the equation of a plane, and using that equation, I can get any point in the plane I want. So I'll call this point P. And it doesn't have to be this point. It could be any point in the plane, right? And now I can form a vector from P to Q. That looks about right. So now we have a vector from P to Q. What should we call it? W maybe? Okay, so this is the vector W. And so what I would like to do then is to find the component of W orthogonal to the plane. Right? So if I draw a vector normal to the plane, right, say this vector n, and of course finding that vector n should not be difficult. After all, you have the equation. You just write down the coefficients, right? A, B, and C. So from the equation of the plane, finding a normal vector is just identifying A, B, and C here. Not hard, right? Oh, so those are that's our normal vector. Okay. And now what I'd like to do is project the vector W onto that vector n. Okay, so that gives you, let's say, this red vector here. This is the projection of W onto n. And that was a couple videos ago, but let's figure out that vector. So you remember the formula? It's okay if you don't. You can look it up. I think I remember it. So I think it's W dot n divided by the magnitude of n squared times n. Right? So yeah, you got to be careful. You're switching your u's and v's, right? So your u is now w and your v is now n. But, you know, when you switch those, you get the same formula. And, right, so now we just take the dot product of those, w and n. Oh, so w is what? W is, so I missed something here. The point P has coordinates x0, y0, z0. Oh, no, sorry. No, we don't, okay. Shoot, how about x1, y1, z1? Actually, just x, y, and z. Could be any point in the plane, right? X, y, and z. Any point that satisfies this equation, any x, y, and z that makes this equation true will be a point in the plane. Okay. So, so the vector W, and I don't know if I have enough space to squeeze it in here, but All right, let's try it. So this is going to be x0 minus x, so it's going to be backwards here. y0 minus y, and I'm going to move this over, z0 minus z. Okay, so that's my w. And then when I take the dot product with n, what do I get? I get a times x0 minus x plus b times y0 minus y plus c times z0 minus z, all divided by the magnitude of n, so that's just the square root of a squared plus b squared plus c squared, and then times the vector n, which has components a, b, and c. Okay, so that is a very odd formula for the projection of w onto n. But I think this was probably not even necessary. We can just take the vector from p to q, right, dot n. These are all given, right? And just divide by the magnitude of the vector n squared times n, times the vector n, right? And remember, all of this is just a number times n. What we're really looking for is not the vector, of course. We're looking for a distance. So how do you find the distance then? It's just the magnitude of that vector. It's the norm of that vector, right? So really, we just need the magnitude of this vector. And luckily, that is just going to be the absolute value, because the dot product could be negative, so let's make it positive. Distance is positive. Absolute value of the dot product of p, q, and n, and then divided by just the magnitude of n. Because what happens is you get the magnitude of n here, and that one of those magnitudes cancel. Right. And so that's it, right? If you do work this out, what you'll get is the absolute value of a times x0 plus b times y0 plus c times z0 plus d, again, all in absolute value, divided by the square root of a squared plus b squared plus c squared. So either one of these, right, you can think of as the distance. Right, so that's your d for distance. And again, it's a formula that's on your formula sheet. It's not one you need to memorize. I probably couldn't remember it either unless I derived it like I did here. Okay, so, and I'm out of space. So that's going to be our formula, and now we'll just do an example. Okay, find the distance between the point Q with coordinates 2, 1, 4 and the plane x plus 3y minus z equals 4. Okay, so the first thing to note is that we're given x0, y0, z0. That's just 2, 1, 4. And we're given a, b, and c. So those will be the components of a normal vector to the plane. It's just 1, 3, negative 1. Right. However, notice that this equation is not quite in standard form. The 4 is on the wrong side, right? So we should rewrite this as x plus 3y minus z minus 4 equals 0. And this is going to be important because, right, d is not 4, d is negative 4. And so it depends on which formula you use for d. Right? If you use this formula, again, we have our n, we have our q, we just need a p. We need a point in the plane. So again, pick any numbers, x, y, and z, that satisfies this equation. So basically, we have a choice of pretty much anything we want here for p. Okay, so make it as simple as possible, right? If x is 4, then y and z are both 0, right? 4 plus 0 minus 0 is 4. So you can easily just pick the point 4, 0, 0. Right? Or if x and y are 0, then z would have to be negative 4. So you can also pick the point 0, 0, negative 4. Right? Or any combination. You can think, wait a minute, 1 plus 3 is 4. Right? So that makes x1 and y1 and z0. So you could pick 1, 1, 0. Again, any one of these points will do it. It does not matter. I'll pick the simplest one, 4, 0, 0. So that'll be my P here. Okay, so the vector from P to Q will be, let's see, 2 minus 4 is negative 2. And then 1 minus 3 is also negative 2. And then 4 minus, oh, I'm sorry, 1 minus 0. Yeah, 1 minus 0 is 1, right? And then 4 minus 0 is 4. So I think I got that right. Yeah, the problem is I got to go between this normal vector. I was getting confused with that. So, okay, so I think that's the vector from P to Q. And by the way, if you did Q to P, if you did 4 minus 2, 0 minus 1, 0 minus 4, you know, you'll get the opposite coefficients, or sorry, the opposite components. The opposite components. And then, you know, that'll still be a normal, I think that'll still work. I think that'll still work. I erased the picture, but that should still work. Okay. All right, and now just take the dot product with n. So just for reference, here's n again, 1, 3, negative 1. So the dot product is negative 2 plus 3 minus 4. So that's going to be negative 3. Yep. Right, and so this is why it's very important to take the absolute value, because the distance, we don't want to say the distance is a negative number, right? It's got to be a positive number. And we also need the magnitude of n. So 1 plus 9 plus 1 is 11. So magnitude of n is 11. So the distance is just 3 over the square root of 11. And if I haven't told you this already, you don't have to rationalize the denominator. So I'm fine if you leave it like this. If you do rationalize the denominator, you just get 3 square root of 11 over 11. So I would be happy with either. And that's the exact distance, right? The formula gives you the exact distance. The approximate is, I'll just use your calculator. And so the approximate distance is not even 1. It's about 0.9045 to 4 decimal places. So again, that's the approximate, but in most cases, I'm just going to want the exact. I know most of you are going to be engineers, so you love approximating things, and that's fine. In math, we usually prefer exact values whenever possible. Right. So that's using the distance formula for a point and a plane. And by the way, if you use the formula here, this would also work. Plus d. Just be aware, though, that your d is not 4, it's negative 4. And if you use d equals 4, you're going to get the wrong answer. So be careful of that. Okay, so now we need the distance between a point and a line. Okay, so let's draw a line. I'll call it L. So the line could be given either as a set of symmetric equations or parametric equations. Let's suppose they're given parametrically, just for convenience. And if they're given symmetrically, you can always convert to parametric form. That's not hard to do. Okay. Now be careful. A, B, and C, of course, is a direction vector for the line. It points in the direction of the line. Okay. There is no such thing as a normal vector to a line. Well, okay, of course there's a normal vector to the line, right? There's this, let me do a little bit better job than that. Right, so any vector perpendicular to the line is a normal vector. But that's certainly not the only one. Right? This is also perpendicular to the line. Right? This is my right angle here, right? This is also perpendicular to the line. So, yeah, you just go completely around the line. The normal vector, there is no the normal vector, it's a normal vector. And so, yeah, so be careful you don't get confused between normal vectors to a plane, which is, at least up to a constant, completely specified. But for a line, there's many normal vectors, and so that's, not helpful. So when you talk about the direction vector, it's the vector pointing along the line, or you can say parallel to the line, but not normal to the line. Okay. All right. So now we have a point. Again, I'll call it Q, and it'll have coordinates x0, y0, z0, yet again. And we want to find the distance between that point and the line, right? What do I mean by the distance? I don't mean this distance, right? Or this distance, or this distance. I mean, this distance here. The shortest distance, the minimum distance, right? So maybe I'll do that in yellow. Right. In other words, if you just go down straight perpendicular to the line, we're looking for that distance there, right? And that is unique. All right, so this time I'm not going to go through the derivation. I'm just going to write down the formula. It's going to be the magnitude of the vector from P. Now, P will be any point on the line. So just x, y, and z, I guess. Right. So you can draw a vector from that point to Q, just as we did for the point to a plane. So it's going to be the magnitude of, well, for the plane it was the dot product. For a line, now we're going to use the cross product. Right. So PQ cross V. And then divide by the magnitude of V. And that's it. You can also use the corresponding formula if you happen to know the angle between the vector from P to Q and the vector V. And again, you can find that angle by just taking the dot product, but that makes it a little more complicated. Right, so let's say that angle is given. Then you can also find the distance by taking the magnitude of the vector from P to Q times the sine of the angle. And of course, that's just trigonometry, right? PQ, the magnitude of PQ is just the length of the vector, the red vector from P to Q. That's the hypotenuse, right? So remember, sine is opposite over hypotenuse. So this formula should make sense as well. Okay, so again, this is distance between a point and a line. Right. Not point P, but point Q. Right. Or let's put it this way. The distance between point P and the line is 0. If the point is on the line, then there's no distance between the point and the line. And the line, again, the line could be given parametrically, or if it's given parametrically, then you know the point, and you also know the direction vector. So this gives you your point P, this gives you your vector V, A, B, and C are the components of that vector. And there you go, there's the equation. Let's maybe do a quick example. And here it is, right? Find the distance between the point Q with coordinates 2, 1, 4, and the line x minus 3 equals 2 minus y over 3 equals z minus 1 over 2. Okay, so notice that I'm giving you the equations of the line in symmetric form. So probably first thing you should do is convert them to parametric form, set them all equal to t, And that will give you what? It'll give you x equals 3 plus t. Y equals, oh boy, we have the minus sign, right? So I think it's going to be 2 minus 3t. Yep. And then z will equal 1 plus 2t. Okay. So there you go. Symmetric form, parametric form, not hard to do. And now we have our point P. Just set t equal to 0, so we might as well use 3, 2, 1 for the point P. And for the vector v, we might as well use the coefficients, right, a, b, and c. It's 1, negative 3, 2. Okay? And so what do we need? We need the vector from P to Q. So remember, Q has coordinates 2, 1, 4. So the vector, well, let's do it right here. The vector from P to Q will have components 2 minus 3, so negative 1. 1 minus 2 is also negative 1. And 4 minus 1 is 3. Okay, so that's the vector from P to Q. So now we take the cross product with V. So maybe I should write V underneath. And now we can take the cross product. Right, so negative 2 plus 9 is 7. 3 plus 2 is 5. And 3 plus 1 is 4. So we get 7, 5, 4 as the components of the vector, PQ cross V. But remember, we only need the magnitude of that. So now just take the magnitude. Usual Pythagorean theorem, right? Or distance formula, right? 7 squared plus 5 squared plus 4 squared. Sorry, 5 squared plus 4 squared. Okay, I get the square root of 90, or if you prefer, 3 squared of 10 to simplify it. And what else do we need? The formula, we need to divide by the magnitude of V. And we never found the magnitude of V. But that's not hard. It's the same formula, right? Just with these components here. So 1 plus 9 plus 4. I know it's negative 3 squared, but it doesn't matter, right? So I think that's the square root of 14. So now just divide, right? The formula for the distance, you divide this magnitude by this magnitude. And of course, they're just numbers, so you get a number. The square root of 90 divided by the square root of 14 is just the square root of 45 over 7, to simplify it a little bit. And, well, the square root of 45 is 3 square root of 5 over 7. Right. Again, I'm not too big on that. I would accept this too. Oh, wait a minute. That's not right either. It's over the square root of 7. Okay. So it's 3 times the square root of 5 over 7, although that almost looks like the cube root of 5 over 7. So let's make the 3 a little bit bigger here. There we go. Or better yet, you can just say 3 times the square root of 35 over 7 if you want to rationalize the denominator. So yeah, the point is I'm fine with any one of these answers here. They're all just as good. Okay, and approximately this should be about 2.5355. These are 5s, not s's. So that's the approximate. Okay, and again, we didn't specify units here, so 2.5 units, right? Whether it's meters or centimeters or feet or inches, we never specified it, so that doesn't matter. So in these cases, the answers will just be pure numbers. So I hope that helps. And we're not done yet. So I think earlier I promised you a problem where we want to find the line of intersection of two planes. So you have two planes. Say here's one plane and here's another plane. Right? They don't have to be perpendicular, of course. I'm just making it easy to see that this line here lies on both planes. So that line is the intersection of the two planes. Okay, so how do we find that line? Or specifically, how do we find the parametric equations of that line? Okay, so, right, so, let's say the red plane is the top equation and the green plane is the bottom equation. Again, they're probably not normal, they're probably not normal planes, so this is not a, an actual representation of these planes. But, as a rough approximation, suppose that they are. Right? So, yeah, so what do we need to find the line of intersection? Right, so in other words, what do we need to find the parametric equations of a line? Well, we need a point on the line, and we need a direction vector for the line. So we need a point, x0, y0, z0, right? And we need a direction vector, v, that points along the line. I know that's not quite right, but close enough, right? So remember, the vector v will have components a, b, and c. And then you just, once you have that information, you just write down the parametric equations, right? Okay, so I just wanted to clean that up a bit. So first thing to note is that this point, x0, y0, z0, is on both planes. Now, I intentionally didn't draw it that way because remember, the planes go on forever. They extend infinitely in all directions. So if you like, you can think of the point here, but it's a point on the green plane and a point on the red plane. Okay? Right. Now the problem is you can't just say pick a plane and then pick a point on that plane. Right? So we can say, well, look, I can pick x equals 2 and then y and z are 0. So 2, 0, 0 would be a point on, let's say, the green plane. But that doesn't mean it's a point on the red plane either. Is this point on the first plane, right? Well, let's check. If we plug in x equals 2, we get 4 times 2 minus 0 plus 2 times 0 equals 3. We get 8 equals 3, which is definitely not true. So this point P might be on one plane, but it's not on both planes. So yeah, you have to be careful. You have to pick a point that's true for both equations, not just one or the other. Right, so definitely this point P cannot be our x0, y0, z0 because it's only on one plane, not the other. We need a point on both planes. So what can we do here, right? So we can't just pick an x, y, and z. Well, I don't know. I mean, I'm going to have a very hard time trying to figure out an x, y, and z that's satisfied by both planes. And if you can do it, great. But I can't. So here's how I would approach the problem, right? We cannot just pick an x and a y and a z, but we can pick one of those numbers. Right? So we're just going to make an arbitrary choice. I'm going to choose, and we could say x, right? We can say x is 0 or y is 0. I'm going to pick z to be 0, right? And there's nothing magical about 0. I could have picked z equals 1 or z equals, 217. But let's just keep it simple, right? Let's choose z equals 0, right? So if we choose z equals 0, what does the first equation become? It becomes 4x minus y plus 0 equals 3, right? And then the bottom equation, the second equation, becomes x plus y equals 2. Well, you've seen this before, right? This is just a system of two equations and two variables. It's pretty easy to solve that system. right? We can eliminate the y. If we just add the two equations together, we get 5x plus 0 equals 5. And if you divide by 5, that just tells me that x has to be 1. Right? And if x is 1, what's y? Well, plug it in, right? 1 plus y equals 2. Oops, equals 2. So I'm pretty sure that y has to be 1 as well. Right? And it would have worked in the first equation, right? 4 times 1 is 4. 4 minus y equals 3. That tells me that y has to be 1. Right? So if we pick z equals 0, then x has to be 1 and y has to be 1 as well. So this gives us the point 1, 1, 0. Okay. So, and you can double check that this point will be on both planes, right? If you plug it into the first equation, you get 4 minus 1 plus 0 equals 3, which is true. And for the second equation, you get 1 plus 1 plus 0 equals 2, which is also true. Okay. So why does this trick work? Why can't I just pick z equals 0? Well, the reason why that works is this line has to have some z value, right? Unless you're unlucky enough that that line, that the line of intersection, happens to be, say, parallel to the, xy plane or something. So maybe z equals 4 or something like that. So if it lies in that plane, then you can't pick z equals 0. And, you'll see that it won't work out, right? You'll get an inconsistent system. But that's why it works, because at some point on this line, there will be a point somewhere on the line where z is equal to 0. We just don't know where that is until we solve the equations like we did. So that point happens to be 1, 1, 0, right? Or better yet, if z is 0, then let's make it this point right here. Right? So 1, 1, 0. So that is a point that's on both planes. And if it's on both planes, it's on the line of intersection. Okay, so now we're almost done. We have the point, right? We have our x0, y0, z0. And we should erase that one then. Now what else do we need? We need a direction vector. We need a vector v pointing along the line. And how are we going to do that? Well, here's one way. We can easily come up with a normal vector to the green plane. Again, I'll call that n1. And we can find a normal vector to the red plane. I'll call that n2. And so the line, again, this is an optical illusion here, the line should be coming right out of the screen, but it's on a slant here, so, I don't want to use red, because that's for the plane here. Can I use blue? Right, so if we take the cross product of n1 and n2, that'll be a vector v. We'll stick with the purple vector here, a, b, and c. Right. So that's probably the easiest way to do this, is to take, as your direction vector v, just take the cross product of n1 and n2. Okay, so n1 is, well, which one is which doesn't matter, right? Because you'll get a vector maybe pointing in the opposite direction then. But either way, it's fine. So, right, so n1 will be 4, negative 1, 2. Those are the coefficients of the first equation. And then n2 will be the coefficients of the second equation, 1, 1, 3. So when you take the cross product of these, well, you should line them up as a determinant. But I think you get 1, 1, 3. Right? Oh no, I'm sorry. That's the vector n2. All right, let's work it out. Right. So this will just be the determinant ijk. 4, negative 1, 2, and 1, 1, 3. Is that all right? All right. So now for the determinants, you get for the I component, negative 3 minus 2 is negative 5. For the j component, you get 2 minus 12 is negative 10. And then 4 plus 1 is 5. So you can use that as your direction vector. if you want, or just notice that everything's a multiple of 5. So in fact, you can multiply by, or divide by -5, and you just get 1, 2, -1. Right? So it doesn't matter. You can just scale it any way you want. So for my direction vector, I'm just going to pick 1, 2, -1. Right? And now we can write down the equations, right? Our x0, y0, z0, once again, is 1, 1, 0. So now we write down the parametric equations in the usual form. So x0 plus a times t, a is 1, right? Y equals y0 plus 2 times t, so 1 plus 2t. And then z is going to be, let's see, 0 minus 1 times t, or just z equals -t, right? So you don't need the 0 here. So these are the parametric equations. Right. And if you want symmetric equations, just solve for t. So you're going to get, let's see, x minus 1 equals y minus 1 over 2 equals negative z. Negative z. So those are the set of symmetric equations. I know they didn't ask for that, but they could. In a different problem, they might. So just to make sure, these are parametric, and these are symmetric equations of a line. Now, again, this wasn't the only way to do it. You notice that I picked z equals 0. Another thing you could do, for those of you who've had linear algebra, you know that this system here, the original equations, is an overdetermined system, right? So you can set up your matrices, solve that system, and then you'll get a free parameter. You know, the parameter might be t, in which case, right, that would give you that, you know, the equation of the line parametrically in that sense already. So that's another way you could have done this, right, is just use a little bit of linear algebra here. But for those of you who have not had linear algebra, this is a perfectly good way to do it as well. Okay. Okay, I think one last example for this section. This was a long one, but there's a lot of material in it, right? Just to recap, there's parametric equations of a line, the equation of a plane, the angle between two planes, the distance between a point and a plane, the distance between a point and a line, and so on, right? And so, yeah, so this was a long one. I promise the next one will be shorter. In fact, it's really just a bunch of surfaces that we'll talk about. But one last example for this video, I think. And we want to find the point of intersection of the line, and the line is given parametrically, right? A set of 3 parametric equations. And the plane, the equation of the plane, which is in the usual form. Just realize that d is not 20, d is -20. But I don't think it matters in this case, right? Again, where it matters is if you're using the formula for the distance between a point and a plane. But that's not this, right? So, all right, so we have a plane, and we have a line. Presumably the line is not parallel to the plane. If it is, then there is no point of intersection, right? So, oh, sorry, I didn't mean to do that. So presumably what happens is we draw a line, it's going to cross the plane at some point. Right? So if that's the line, it's going to cross the plane somewhere, and the point right here is that point of intersection. Right? So it's going to have an x, y, and z coordinates. What are the coordinates of that point? Okay. Now keep in mind the line might even be, you know, perpendicular to the plane, for all we know, but we don't know that. It doesn't have to be. In fact, you can check that if you find a direction vector for the line and a normal vector to the plane, If those two vectors are parallel, then the line will be perpendicular to the plane. But yeah, I don't think that's the case here. You can prove me wrong, but either way, it doesn't matter, right? So we're looking for the point of intersection. So if you think about it, right, we're looking for an x, y, and z. That's true for the line, right? So this is the equation of the line here. And maybe I shouldn't use green. I should use purple for that. Right? Right. Now, so if you pick a t, you might get a point on the line, but that might not be a point on the plane. On the other hand, if you pick an x, y, and z in the equation of the plane, right, that makes that equation true, well, you could get a point on the plane, but it might not be on the line. So again, just picking numbers here I don't think is going to work. Right? In some sense, what we want to do is intersect them, right? We want the x, y, and z here should be the same x, y, and z here for the equation of the plane. Right? So I hope that gives you the right idea here. All we're going to do is substitute this expression for x and just plug it into the equation of the line, right? Likewise, this expression for y, we'll plug it into the equation of the, sorry, not line, plane. And then this expression for z, we'll plug that in here. So what happens when we do that? We get 4 times 2 plus 5t minus 3 times y is 1 minus t, and then plus 5 times z, and z is 3 plus t, right? And then minus 20 equals 0, or this just equals 20, either way. So notice what you get. You get an equation in t. So what do you think you should do? Of course, solve for t. Right, so let's do that, right? We multiply this out. We get 8 plus 20 times t minus 3 plus 3 times t plus 15 plus 5 times t equals 20. All right, so 23 plus 5, we get 28 times t. And then 8 minus 3 is 5. 5 plus 15 is 20 equals 20. Oh, so 28 times t, when you subtract the 20, you get 0. Divide by 28, we get t equals 0. Okay, that can happen. Again, that's just a coincidence, but in general, you could get anything. You can get t equals 5, you can get t equals, 2 over 37. It could be a horrible fraction, but it's going to be some value for t. Okay. Now, of course, that's not the answer, right? That's not the answer to the question. The question isn't find t. The question is to find the point, right? And a point has x, y, and z coordinates. But look, it's a point on this line, L. And I've already sort of botched all the equations here, but let me just write down the equations of the line again. So I think you know what to do. Plug in the t into this set of equations, and that'll give you your x, y, and z. Right? So obviously, if t equals 0, when t is 0, you just get the point x equals 2, y equals 1, and z equals 3. So our point P has coordinates 2, 1, 2, 1, 3. Sorry, not negative 3, positive 3. So that's the point of intersection. Now, of course, we could have guessed that. I mean, you could have said, well, suppose t is 0, then this point will be 2, 1, 3. But remember, by picking a t, you're getting a point on the line. There's no guarantee that that point will also be on the plane. Right? Certainly if you pick any other t, if you pick t equals 4 or t equals 1, right, or negative 1, all of those values of t will give you a point on the line, but it will not be on the plane. The one specific value of t that also guarantees that that point will be on the plane happens to be 0, but again, that's a coincidence for this particular problem, and maybe it made it a little easier than it had to. But in general, yeah, you substitute the expression for the lines into the equation of the plane, solve that equation for t, and then plug that value of t into the equations for the line, and that'll give you the one point that intersects the plane and the line. So I hope that helps. And these are the typical types of homework problems. And in fact, we're going to see intersecting a line and not just a plane, but any surface. We can do that for other types of surfaces, not necessarily planes. But it's the same procedure. It's the same idea as we did here. So I think that should do it. So we'll end it here, and then we'll go on to quadric surfaces in the next video.